Hey guys, welcome. So today we will have a special recitation. So this will be delivered by Jack. He will solve a couple of problems regarding differentiability. Okay, Jack, you can go ahead.
All right, so this first problem we're going to do is from Putnam A1 2016. And what we're supposed to do is find the smallest integer k such that for every single polynomial with integer coefficient, so every single polynomial p of x with integer coefficients, and every single integer j, where you're supposed such that the kth derivative of p evaluated at j equals, right, and this is just the notation for the derivative, the jth derivative, right? So this could just be rewritten as dk over dx k of p of x, and then we're just going to evaluate this whole derivative at x equals j, right? So what we're trying to do is find some integer k here that is the smallest possible, sorry, this should be positive integer, right? So we have to find this k right here to be the smallest positive integers such that for any single polynomial p we choose and any single integer, the kth derivative of that arbitrary polynomial evaluated at that arbitrary integer is divisible by 2016, right? So we would have to show that any single polynomial evaluated at, once we take its kth derivative evaluated at j, it becomes divisible by 2016, right? So let's just look at maybe some example polynomials to see what we're working with and if we can gain any information from that. So a good polynomial to start off with would be, thinking of this one, let's just call it q of x, which would be x to the power of k, right? And so whatever k happens to be, right, we're just going to choose this polynomial. So let's look at the kth derivative of this, right? So if we take the kth derivative of this polynomial here, well, that's nothing more than k times k minus 1 times k minus 2 all the way down to times 2 times 1, right? Because just using the power rule for derivatives, you just drop the k down, it becomes k minus 1, and you keep doing that k times. So all we're left with is just k factorial as the kth derivative of this polynomial right here. And then, of course, when we evaluate this polynomial q, its kth derivative at j, we just get k factorial because the kth derivative of q does not depend on x, right? It's just constant. So in order, the next step would be to look at this polynomial we have right here and determine when it's divisible by 2016, right? Because we have to find the smallest k such that any polynomial, when evaluated at j, is divisible by 2016. So this is a particular polynomial we have here, and a particular, we've chosen a particular j here. So we have to see exactly when this polynomial is divisible by 2016. And if we just sort of look at it, right, we have that if k were to be 1, then k factorial is again 1, and 1's not divisible by 2016. So we have that whatever k is, it has to be greater than 1. And well, we can keep on doing this, right? We can check k equals 2, and k factorial in this case is just 2. Again, not divisible by 2016. And we can just keep going through this and checking the factorial to see when the first case of k being divisible by 2016 is. And this happens to be at k equals 8, right? So at k equals 8, we have that, what is it? It's this number right here, right? So that's k factorial. And this right here is divisible. It is divisible by 2016, right? And this is the first instance of it. So for k equals 1 all the way up to k equals 7, the k factorial is not divisible by 2016. So k equals 8 is the smallest positive integer such that k factorial is divisible by 2016. So that means that maybe if we set k to be 8, that would be a good starting point to see whether maybe that's the actual k we're looking for, right? Because it seems to work for this polynomial, so maybe it could possibly work for more. So let's go into trying to prove that actually k equals 8 is the right choice. So let's let p of x be an arbitrary polynomial with integer coefficients, right? And let's let n be the degree of the polynomial p of x. So first case, if n is less than 8, right? So if n's less than 8 and we take the kth derivative, in this case we've chosen k to be 8, right? So if we take the 8th derivative of p of x, well, that's just going to be 0, right? Because the highest power in this case is something less than 8. So if we take 8 derivatives, we're going to end up with a 0 polynomial, right? Because if we go back up here to our original problem, all we're supposed to do is evaluate our polynomial at k, and we're suspecting that k is going to be 8. And we get that this derivative is 0, and clearly 0 is divisible by 2016. So if the degree of our arbitrary polynomial right here is less than 8, then everything works. So now the only other case to check is when n is greater than or equal to 8, right? So that's going to be the next part, and that's a bit harder. So let's go ahead and do the next case. So if n is greater than or equal to 8, right? That means that p of x is going to look something like this. It'll be, let's say it's pn times x to the power of n plus pn minus 1 x to the power of n minus 1 all the way down to p1 times x plus p naught, right? Where each one of these, where each one of these pi's are just integers, right? Because p is a polynomial with integer coefficients, so we're just letting it be whatever this is. And remember that in this case, we have that n is greater than or equal to 8. So this is a polynomial with at least 8th degree. It could be bigger, it could be 10th degree, right? So let's try and just take the 8th derivative of this and see what we get. So if we go and take the 8th derivative of this polynomial here, actually first, before I do that, let me rewrite this polynomial in a way that's a bit easier to work with notationally. So p of x, if we just write it in summation form, right, is just the sum from I equals 0 up to n of pi x to the power of I, right? So where each one of these individual terms is just the terms we see up here, right? From 0 all the way up to n. So now that we have it in a way we can easily take the derivative of, let's go ahead and do that. So taking the 8th derivative of this polynomial here, it'll just give us a sum from I equals 8, because remember, all of these terms right here, all of these ones right here that are less than 8, right, where this is the 0th term, this is the first term, and so on. The terms that have degree, these terms here that have degree less than 8, when we take the 8th derivative, it's just going to be identical to 0. So we no longer need to count them in our sum. So we can start at I equals 8 because that's going to be our first non-zero term. Because if I is less than 8, that means x is to a power less than 8. So after taking 8 derivatives, it'll become 0. And then, of course, it's going to go up to the nth term. And what we'll have is pi times I minus 1 times I minus 2 all the way to I minus 7 times x to the power of I minus 8, right? So that's what each term is going to look like after we do the 8th derivative on it. And this right here is, let's see. Okay, so this is just the polynomial, right? This is just the polynomial after taking the 8th derivative. But back in the original problem, now we just need to evaluate that polynomial at our j, right? And remember that this j is just some arbitrary integer. So we have to now evaluate this polynomial at j. So that's pretty easy right here. We just have to plug that in. So it'll be from I equals 8 to n of pi times I minus 1 all the way to I minus 7. Instead of x here, now we're going to write j to the power of I minus 8, right? So we have to show that this number right here is divisible by 2016. And if it's divisible by 2016, then we're done. And we found our smallest k, and it is 8. So let's see if we can notice anything with these coefficients, right? So if we look at it, it almost looks like we have a factorial, I factorial here, right? We have I minus 1 all the way to I minus 7, and we're just missing some bits. So one thought you could do is sort of look at this and see if we can maybe rearrange it in such a way that we get something that we know is divisible by 2016, right? So let's just have our pi out front. And let's first off start by filling in, let's see, let's go and fill in the rest of the terms up top, right? So let's do I times I minus 1 all the way to I minus 7, I minus 8, all the way down to 2 times 1, right? So now we have I factorial up top. And then down on the bottom, let's put, we have to have I minus 8 times I minus 9 all the way to times 2 times 1, right? Because we just added we just multiplied by this, the remaining part of the factorial and the remaining part on the bottom, so we still have equality, right? And then we can't forget our j. Those used to be j to the power of I minus 8. And now we see that up top, we just have I factorial, right? So we have I factorial on the top. And then let's see if we can do anything to the bottom here. So what I'm thinking when I see this I factorial up in the numerator is maybe we can somehow relate this coefficient to the binomial coefficient, right? And just a refresher for what that would look like. The binomial coefficient, n choose, m choose L, right, is nothing more than m factorial over L factorial times m minus L factorial, right? And we already have the I factorial on the top. So maybe we can rearrange this a bit to make it look like this right here. So let me just turn on do not disturb. There we go. All right, so let's see. We have that right here. This right here is exactly what we have right here, this m minus L, where m is taken to be I and L is taken to be 8, right? So this bottom part right here is just I minus 8 factorial. And all we would need is to put an 8 factorial down here. And then to keep the equality, we have to put an 8 factorial up on the numerator, right? And then we have times j I to the 8th. And then, of course, let's just rewrite this, make it all nice and neat. We have pi times I choose 8 times 8 factorial j to the power of I minus 8. And let's just make sure we haven't done anything bad so far. This right here, this binomial coefficient is always an integer, right? Since I and 8 are integers, this is going to be an integer. So we know our whole coefficient's still an integer. And we have this 8 factorial here. And if you recall, back to the beginning of the problem, let's see, where is it? Right here. When k equals 8, 8 factorial is divisible by 2016. So we have that this right here, each coefficient here is this part right here is divisible by 2016. So that means the entire sum will also be divisible by 2016. And we're done, right? So that means k equals 8 does satisfy this property up here. And we can see that for any k less than 8, we have a clear counterexample, that of course being our constructed q of x.
Yep. Very nice.
All right, and then let's see the next problem.
It was easy, right? How did the problem seem to you? Like, easy, huh?
Oh, the first one?
Yeah, this
Yeah, the
one.
first one was pretty easy. This second one, I got caught up on taking the derivative multiple times trying to find a pattern.
Okay.
but I eventually found a better way of doing it. But it was a lot of computations at first. So this second one states that we're going to let...
Right, Putnam, what kind of problem is?
Oh, yeah. This one is, what is it? It's Putnam A1 2002, I want to say. And it states that we're going to let K be, here, we're going to let K be a positive integer. And we're given that the nth derivative of the function 1 over x to the power of k minus 1 has the form p to the power n, p sub n of x over x to the power of k minus 1 n plus 1, right? So that basically states that like the nth derivative of this right here is going to be of the form this function here, where p sub n of x is just some polynomial, right? Where p sub n of x is a polynomial. And what we're tasked with doing is we have to find p sub n of 1, right? So whatever this p sub n is, we have to figure out what it looks like when it's evaluated at x equals 1. So like I was saying earlier, what I originally did was take the derivative of this multiple times and then put it into this form and try to see if I could see a pattern with these p sub n's. That was a lot of work, and I didn't get very far with what I was trying to find, right? I couldn't really find any patterns with that.
So basically, you just tried to find the polynomial, the Pn of x?
Yeah.
Write it explicitly.
Yeah.
Well, it's kind of tempting.
That was really hard. So I stopped and then tried a different approach. So instead, what I decided to do was maybe come up with instead of an explicit way of representing p sub n, instead try to find some sort of recursive relation with p sub n and its previous terms, like p sub n and p sub n plus 1, right? Try to come up with some sort of recursive relation. So what I did was we're going to go ahead and take the derivative of p sub n of x over x to the power of k minus 1 to the n plus 1, right? And what this is going to be, it's going to contain the p sub n plus 1th polynomial, right? Because this is going to be the this right here is going to be the n plus 1th derivative of our original function here. So that means it's going to involve p sub n plus 1, right? So we'll have an equation that hopefully relates p sub n to p sub n plus 1. So let's just go ahead, do the computations, and compute this derivative, right? Typical calculus stuff. We just have that the derivative of this is going to be p sub n prime of x, where p sub n prime is the derivative of p sub n, times the denominator, which is x to the power of k minus 1, n plus 1. Let's see, and then we're going to subtract p sub n of x And now we have to multiply it by the derivative of the polynomial here on the denominator. And that's going to be n plus 1 times x to the power of k minus 1 to the power of n. And then by the chain rule, we have to take the derivative of this inside function now. And the derivative of the inside function is pretty easy. It's just k times x to the power of k minus 1. And then I believe that is all correct. And then on the denominator, we just get x to the power of k minus 1, 2n plus 2. Okay, so the next step is trying to put what we just computed here into this form up here. So let's go ahead and jump into that. Let's see what we get. So we have, very first thing I notice, we can factor out a x to the power of k minus 1, and we can factor it out n times because we have n plus 1 here and n of them here. So let's factor that out. We have x to the power of k minus 1 to the power of n, and that's all going to be multiplied by n prime of x times x to the power of k minus 1 minus p sub n of x times n plus 1 times k times x to the power of k minus 1. And then on the denominator, all we have is the same exact thing, xk minus 1, 2n plus 2. And then we're just going to go ahead and cancel this out with our denominator here. And we'll get that we'll have pn prime of x times x to the power of k minus 1 minus k times n plus 1 times pn of x times x to the power of k minus 1. And that's all going to be over. And then remember, we canceled this out here. So we just have to subtract an n from this power up here. And we have x to the power of k minus 1 n plus 2. Okay, so now this is great, right? Because look at this right here. We have an n plus 2 here and some polynomial up here.
Mm-hmm.
That's exactly what our problem told us, that the n plus 1th derivative of this function is. So the problem states that the n plus 1th derivative of this is p sub n plus 1 all over x to the power of k minus 1 to the power of n plus 1 plus 1, so n plus 2. So that means that p sub n plus 1 of x equals p sub n prime of x times x to the power of k minus 1 minus k times n plus 1 times p sub n of x times x to the power of k. So right here we have a relationship between p sub n plus 1 and p sub n. The only problem with this right here is, of course, this p sub n prime. But as you can see, that'll actually go away because back in the original problem, it only asks us to find what p sub n is evaluated at 1. So we don't have to worry about anything else.
Yep.
So let's go ahead and evaluate p sub n plus 1 of x at 1, right? And once we do that, we see everything becomes very nice, right? Because here p sub n prime of 1 times 1 minus 1 minus k times n plus 1 p sub n of 1 times 1. And of course, 1 minus 1 here, that's just 0 minus k n plus 1 p sub 1. And so we're left with k times n plus 1 p sub n of 1. Okay, and right here we just have a fairly straightforward recursive relationship. And these are fairly easy to solve. All you have to do in this one is just use a simple induction on n, right? Because we have our recursive formula right here, right? P sub n plus 1 of 1 equals negative k n plus 1 p sub n of 1. And we also have that p sub not of 1, right? Where this means don't take any derivatives. So this means don't take any derivatives. What is the polynomial evaluated at 1? Well, we know exactly what the polynomial is. The polynomial is this thing, this 1 up here. And of course, 1 evaluated at 1 is just 1. So p sub naught of 1 is 1. So we have our recursive relation here and an initial condition. And this is enough to actually go ahead and solve this recursive relation and find what p sub n of 1 is. And if we are to go and just maybe sketch some values of what this is so we can get a grasp of what the pattern is going to be, right? So we know that p sub naught of 1 is 1. P sub 1 of 1 is just going to be, let's go ahead and use our formula. So it's going to be negative k times n plus 1. Sorry, not n plus 1. Here, let me do it this way. We're going to have, here we'll have n equals 0, or, well, okay, I'll do it like this. So we have p sub, n equals 0. We have p sub 1 of 1. So p sub 1 is going to be negative k times 0 plus 1 times p sub 0 of 1. And p sub 0 of 1 is just 1 up here. That was our initial condition. So we just get negative k, right? Because this right here is 1, this is 1, so we're left with negative k. So now let's look at p sub 2 of 1. That's again going to be, this will be the n equals 1 case, right? So p sub 2 of 1 is going to be k times 1 plus 1 p sub 1 of 1. And let's see, this will be negative k. 1 plus 1 is 2. P sub 1 of 1 is, we just calculated, it's negative k. So we have k squared. Sorry, we have, let me write it this way, 2 times k squared, right? And then let's do the next case, n equals 3. P sub 3 of 1 is negative k. Oh, sorry, n equals 3. I skipped a step. It should be n equals 2. Yeah, there we go. So n equals 2. So we have 2 plus 1. P sub 2 of 1. And this is just going to be negative k times 3 times 2 times k squared. So we'll have 2 times 3 times negative k cubed, right? And then let's do another one just to sort of cement the pattern here. So n equals 3. That's going to give us p sub 4. And that will be negative k times 3 plus 1 p sub 3 of 1, which is negative k times 4. P sub 3 is 2 times 3 times negative k cubed. And of course, this is just 2 times 3 times 4 times k to the 4th, right? And if we look at this, we sort of see the pattern starting off, right? So here we have a 2, and then we get 2 times 3, and then we have here 4 times 3 times 2. So maybe the relation has some sort of factorial in it with these numbers here. And if we look at the k, we get k to the power negative k, then k squared, negative k cubed, and then k to the 4th. So we can sort of see a pattern happening right here. And we can claim that p sub n of 1 is going to be n factorial times negative k to the power of n, right? Because if we look at this, p sub, so if we plug in, let's say, p sub 0, right? P sub naught, if we plug in that, we get 0 factorial will be times negative k to the power of 0. Well, that's just 1 times 1, which is 1. And if we do p sub 1 of 1, let's see, that will be 1 factorial times negative k to the power of 1, which is nothing more than negative k, which is exactly what we got up here. And let's do a slightly more interesting one. Let's try p sub 3, right? That's the largest one we did. So that'll be 3 factorial times negative k 3, and that's just 2 times 3 times, let's see, negative k cubed. And we can see that up here, that's exactly what we got, right? So maybe that this would be a good choice, and it turns out it is. It's actually true. You just have to prove it using induction. I don't know if you want me to go into the whole induction proof, but it's fairly simple.
You can, no, you don't have to go like, you can say by a simple induction we can prove.
And then that's the whole problem, right? We found our answer right here.
Yep. Yep. Very nice. Very nice.
And
there was another one, right? If I remember correctly.
The last one. This one's pretty fun. I like this one. All right. So this one here involves
the Taylor series?
Yeah, it's the Taylor series one. Taylor series and a little number theory here. So I don't remember which Putnam this one comes from.
I think it was 2015, if I remember correctly.
Or wait, is either 2015 or 2016?
Or no, 16, you're right.
Yeah.
I think I put it in my worksheet. I think it was
it's problem 22, if that helps.
22. Yeah, it's 2014, A1, Putnam A1 2014.
Oh, 2014, okay. So this one is Putnam A1 2014, and it states that we have to prove that every polynomial, that every
non-zero
coefficient of the Taylor series of this function right here, 1 minus x plus x squared times e to the power of x, so that every single non-zero coefficient of the Taylor series of this right here, about x equals 0, is rational. And not only rational, but whose numerator is either 1 or it's prime in reduced form. right? So if you look at all of the coefficients for the Taylor series of this, they're all going to be rational numbers. And if you simplify that rational number to smallest terms, its numerator is either going to be 1 or it's going to be a prime number. So that's a pretty interesting result, right? That this right here sort of would be a polynomial of, a Taylor series of where its coefficients are either 1 or they're prime, right? Times some sort of rational number, of course. But let's go ahead and prove that this is true. So let's start off by just looking at what the Taylor series actually is. So 1 minus x plus x squared times e to the x. And if you recall back from calculus, the Taylor series of e to the x is just the sum from n equals 0 to infinity of x to the power of n over n factorial, right? So let's go ahead and use that here. We're going to have 1 minus x plus x squared times the summation of n from n equals 0 to infinity of x to the power of n over n factorial. Okay, let's go ahead and move this right here into our sum so we can sort of get a glance at what these coefficients are going to look like. So we're just going to move that. We're going to distribute that over, and we'll have x to the power of n over n factorial, and then we have to do minus x to the power of n plus 1 over n factorial plus x to the power of n plus 2 over n factorial, right? And if we look at this, all this is multiplying this by 1, we get this, multiply this by negative x. So we just add another x up into the numerator. And then finally multiplying this by x squared, hence the plus 2 up there. And what we want to try to do is consolidate this entire sum into a sum where each individual term in the sum is just a singular power of x. Because right now we have the nth power, the nth plus 1 power, and the nth plus 2 power. We want to try to rewrite this in a way that we get rid of these other powers and we just have x to the power of n. That way we can look at the individual coefficients of this Taylor polynomial. So to do that, let's sort of get a feel for what this actually looks like by expanding the sum. So for the n equals 0, we have 1 minus x plus x squared. And then for the next term, this is going to be n equals 1. So we'll have x, and then we're going to have minus x squared. And then we'll have plus x cubed. And then let's do the next term. And that's going to start off with, this is going to be n equals 2 right here. 2 factorial, of course, is just 2. Still pretty simple. So we have x squared over 2 minus x cubed over 2 plus x to the 4th over 2, right? And this is just going to keep going. So let's see if we can notice any sort of pattern here. Well, if we sort of look at it.
Over there, right?
Hmm?
I don't see it, but it's a plus, okay. Between the second and the third one.
The third one?
You see the third parentheses. You see the, I don't see exactly. Anyway, it's a plus. Keep going.
Oh. All right. So if we just sort of if we look at these first two terms here, right? We can see that we get some cancellations because we have a negative x and then a positive x and then a positive x squared and then a negative x squared, right? And then unfortunately, that pattern of cancellation does not repeat because if we look at the x cubed term, this positive x cubed here and this negative one here don't cancel out because this is only half of x cubed, whereas this is a full x cubed. So unfortunately, we can't just say that this is telescoping and that the majority of the coefficients are actually 0. But these first few ones right here are going to be 0. The x to the power of 1 term and the very first non-zero term will be x to the power of 2, and this will be the first one, right? Because in the next, all the terms greater than this one here, the powers of x are going to be greater than x squared, because the next term will start off with x cubed. So this is going to be our only x squared value after we cancel out these two right here. So this is just going to reduce down to 1 plus the sum from n equals 2 to infinity of 1 over n minus 2 factorial minus 1 over n minus 1 factorial plus 1 over n factorial times x to the n, right? You can find this just by sort of playing around with a polynomial a bit, and this happens to be true, right? We can just justify it real quickly to ourselves to make sure that it should even make sense. So here we're starting with n equals 2 down here because the n equals 0 case is right here, right? Our only term with our only constant term is going to be 1, and then our terms with degree 1, as we stated earlier, the only time that appears is up here and right here, and those two cancel each other out, so there's not going to be any degree 1 terms. So we're going to go ahead and start with degree 2. And if we just sort of plug this in and see what we get, we'll have here, when we plug in n equals 2, we get 2 minus 2, which is just 0. So we'll have, this will be 1 plus 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial times x squared, right? So that means that we'll have a 1 plus x squared minus another x squared plus an x squared over 2, and then of course more terms. And if you see right here, we have our positive x squared, our negative x squared, and our x squared divided by 2. And if you look at that, right, and if you try to do n equals 3, you see that the first instance is going to be this one right here. And then we're going to get this one. And then we'll need another one, the other x to the power of 3 term. And that's, of course, going to be the first one in our next term over here, right? So if I were to write that out, it would look something like x cubed over 3 plus x to the 4th over 3, minus plus x to the 5th over 3, and we keep going, right? So as you can see here, we're sort of choosing the powers of x from each of the 3 times it'll appear, because it'll only appear 3 times, and then it's never going to appear again. So here we have x squared, x squared, x squared, x cubed, x cubed, x cubed. And that's exactly what we're getting over here. We're just taking each of these terms from here and just writing them all under the same power of x. So now that we have our Taylor series in a nice form, right? Because we have it that 1 minus x plus x squared times e to the power of x equals 1 plus the sum from n equals 2 to infinity of 1 over n minus 2 factorial minus 1 over n minus 1 factorial plus 1 over n factorial times x to the power of n. So now we have that this is in a form that we can actually try to take a closer look at the coefficients for each one of these x's. The very first coefficient, this one right here is a 1, so it's good, right? Because remember in our original condition, the coefficients either have to be, the numerator either has to be 1 or prime, and of course, the numerator of 1 in reduced form is just 1. So that's good. Now we have to check the hard part, these coefficients here. So let's look at what the coefficient will sort of look like, right? Because right now we have it as a sum of fractions. Let's try to consolidate all of that into a singular fraction. So we have n minus 2 factorial minus n minus 1 factorial plus 1 over n factorial. And that's just going to be find a common denominator, right? And we'll get, let's see, n times n minus 1 over n factorial minus, the next one just needs an n, so n over n factorial plus 1 over n factorial. And now that we have a common denominator, we can actually add these up. And let's see, we'll get n times n minus 1 minus n plus 1 over n factorial. And now let's continue this and see if we can get something nice. So we have n squared minus n plus 1 over n factorial. And that'll just be n squared minus 2n plus 1 over n factorial. And that'll just be n minus 1 squared over n factorial. And of course, that just leaves us with n minus 1 over n times n minus 2 factorial, right? Because right here, we're just going to cancel out a single one of these n minus 1 terms up here with the n minus 1 term that appears here. Okay, so now we have this right here. So this is what our coefficients are going to be in our Taylor series. So what we have to prove is that when we put this into lowest terms, that the numerator is going to be prime, right? So here's where the fun bit happens, right? Let's go ahead and just list out some n so we can get a feel for how this coefficient is working. So let's just get a chart out here real quick. So we have n, and let's see. So first off, for very first n equals 2, because remember that this sum's going to start at 2, is going to be, let's see, 2 minus 1 is 1, and that's going to be over 2 times 2 minus 2 is 0 factorial, so that's just 1/2. N equals 3, that's going to be 2 over 3 times 1 factorial, so that's 2/3. N equals 4. Let's see, we get 3 over 4 times 2 factorial, and that'll come out to be 3/8. And then let's do 5. That'll be 4 over 5 times 3 factorial, and that'll be 2/15. And let's try 6. That will be 5 over 6 times 4 factorial. And that will come out to be 5 over 144. And let's do one more for good measure, right? Let's do 7. So that's going to be 6 over 7 times 5 factorial. And that'll be, let's see, 1 over 140. Okay, so if we look at these right here, for n equals 2, in reduced form we have a 1, so that's good.
Mhm.
N equals 3, in reduced form we have 2, which is prime, so that's good. The next one, 3, that's prime, so we're fine. 5, 2, 2's prime, we're good. 6 is 5, and that's prime, so we're good. And 7 is 1, and of course 1 is also good as well. So if we sort of look at this closely, if we look like back at our original thing right here, if you notice, if n minus 1 is prime, that means it's going to share no common divisors with n or n minus 2 factorial, because n minus 1 is prime. If it shared a common divisor with one of these, then it wouldn't be prime. So that means that if n right here is 1 bigger than a prime, then this fraction right here will already be in reduced form, and the numerator will be prime. So we can see that with these few examples here, we have, let's see, we have 6. 6 is 1 more than a prime. And when we put it into reduced form, we can't actually reduce it any, and we just get a 5 on the numerator. And that's because 6 is 1 more than a prime number 5. Right? So that is going to hold for all n minus 1. Right, if n minus 1 is prime, if this right up here is prime, then this whole fraction will be in reduced form, and we're done, right? So let's just go ahead and write that down. So if we have, so if n minus 1 is prime, then we have that n minus 1 over n times n minus 2 factorial is in lowest terms. Since n minus 1 is prime, and n minus 1 is prime, so that validates what we're trying to prove. So now we just need to do the case where n minus 1 is composite, right? So that means it's not prime. So all these other cases. So if it's for all of these n that are not 1 more than a prime number. And this case is a bit harder, right? But it's not too terribly difficult. But before we go into it, there's a few outline cases that we're just going to do by hand. We've actually already done them. It's going to be the cases right here, the case n equals 2, and the case n equals 5. These are going to be outline cases, and they won't fall into the pattern that I'm about to explain, so I'm going to leave them out. But we can clearly see that they do result in either ones or primes in their numerator, so they're good. But I'm going to not consider them in the next case just to make things easier for us. So our next case is that if n minus 1 is not prime, and that n is not equal to 2 or 5. So what does this mean? Well, if we go up to our chart here, let's see. We have that 2 is accounted for. 3 right here is 1 more than a prime, so it's accounted for. 4 is 1 more than a prime, so it's accounted for. 6 is 1 more than a prime, so it's accounted for. So that means that this right here, this statement right here can be equivalently stated as if n minus 1 is not prime and n is greater than or equal to 7. Right? Because we've thrown out these two cases, we can now assume that n is going to be greater than 7 because we've checked all smaller cases. These ones right here were checked in the first case, and we did these ones here by hand. And you'll see very soon why I had to do these ones by hand. So let's get into it. So right here, we have, we're going to have this result that n minus 1 factorial is congruent to 0 mod n. And this is true for all n greater than or equal to 1. Right?
Mhm.
And this is just a simple result from number theory. I don't know if you want me to go into the proof of this.
No. Come on.
Okay. But
We've done this. Like, did we?
I don't know. Maybe? I don't remember.
Okay, you can say a few words if you want.
Okay. Well, let's see. To actually prove this, it's just done in 2 cases, right? I won't go into the full thing, but I'll maybe just sort of sketch it out. First, assume that n can be written as the product of 2 numbers, a and b, right? So assume it can be written as a and b such that 2 is less than a, which is strictly less than b, which is less than or equal to n minus 1, right? So in this case here, we see that a doesn't equal b, and that neither a or b are n or 1, right? By this stipulation here. So a can't be 1 and b can't be n.
Yeah.
And you can see from this that that's going to imply, this will imply that n minus 1 factorial actually contains both a and b in its product, because both a and b are less than n minus 1. So that means they're somewhere in this product. That means that n is somewhere in this product. Therefore, if we take this mod n, it comes out to 0.
Mhm.
And then the other case is if instead n cannot be written as the product of 2 distinct numbers that are not 1, then it must be able to be written as a prime squared, right? So that's the only other case. If it can't be written like this, it must be written as a square of a prime. And sorry, this isn't for all n. It's for all n greater than 4, right? Greater than 4. Yeah. And then in this case right here, we have that we'll also have the same exact implication, since we have that n's greater than 4. Since n's greater than 4, that implies that p must be greater than 2, right? Because if p was 2, that means n would equal 4, and that goes against one of our given conditions up here. So we know that whatever the prime is, it has to be greater than 2. Therefore, we have that p, which is less than 2p, which is less than p squared, which equals n. And we get this inequality, right, because we're just multiplying by 2. And we get this one because the square is going to be larger than the double, because we know that p is going to be greater than 2.
Yep.
And that, of course, means that both p and 2p appear in the product n minus 1 factorial. So that means n appears in that product. So therefore, if you take it mod n, you, of course, just get 0.
Mm-hmm.
So that's the number theory part of this, right? You just need this result, and we'll go ahead and we'll use it right now. So we have that, let's go back to our case. We have that n minus 1 is not prime and n's greater than 7. And now you can see why I had to throw out the case of 5. Because if I included the case of 5, I'd run into this problem that this result is not true because of this right here. So if we have n minus 1 greater, right, if n minus 1 is 5, that means n is 4, right? So that's why we have this right here, because of this implication.
Mm-hmm.
So let's go ahead and try to actually solve this. So if we look at our original fraction, so n minus 1 over n times n minus 1 factorial. So by the result that we just sort of sketched out, this one up here, instead of using n, if we use n minus 1, we'll get that n minus 2 factorial, right? Because we're going to use n minus 1, so we'll have 2 minus 1, so minus 2 is going to be congruent to 0 mod n minus 1. And this will, of course, be true for all n minus 1 greater than 4. Therefore, n greater than 5. And see, that's where that's why I had to earlier do the n equals 5 case by hand.
Mm-hmm. Mm-hmm.
And then equals 2 case because of this right here.
Yeah.
And then let's look at this. This number theory result right here immediately implies that n minus, oh, sorry, I wrote this down wrong. That should be an n minus 2 factorial. That immediately implies that this n minus 2 factorial, it is divisible by n minus 1. So if we just put this fraction into reduced terms, it's going to come out to be something of 1 over n times some number, let's call it m, right? Where m equals n minus 1 over n minus 2 factorial. And we know m's an integer because we have this right here. So since n minus 2 is congruent to 0 mod n minus 1, that implies that m, which is equal to to n minus 1 divided by that factorial, that implies that m's an integer, so that we have that this original coefficient, when put into lowest terms, has a numerator of 1. And now we have covered every single coefficient, and that's it.
Nice. Very nice. Wow. Great job, Jack. Okay. I think those are the problems, right? 3 problems.
Yeah.
All right. All right. Thank you very much. Let me